Okay, so we're going to look at example 3 here. And example 3 says, find area. So find the area under graph of f of x equals x over 0 to 4. And the book says do it 3 ways. The book has us show part A that we're going to do it using geometry. And then the book's going to have us do limit as n approaches infinity of the right endpoint approximation. And we're going to show that that gives us the same answer that we got using geometry. And then we'll show the limit as n approaches infinity of the left endpoint approximation also converges to the same area under the curve that we get using the other methods. So using geometry, y equals x is just the diagonal line through the origin. If we go out here to 4 units out, it makes a triangle with base 4 and height 4. So we get the area would be 1/2 base times height. So that's half of 16, which would be 8. So using geometry, that's the real quick way we get that, okay, we know the area under the curve is a triangle, base 4, height 4, it's going to have area 8. So now we want to get our Rn notation and we want to work on that. So Rn equals delta x series of j equals 1 up to n f of a plus j delta x. For this, delta x is going to be the interval length, so I'm going to do some scratch work in a different color here to figure out delta x, because we're going to use the same delta x for Rn as well as the left endpoint approximation Ln. So it's the interval length 4 minus 0 divided by n, the total number of intervals we're going to use. So we get 4 over n is our delta x. So my right endpoint approximation equals 4 over n, sum of j equals 1 up to n, f of a is actually 0 in this case. That's a. Do that in a different color so it's clear what we're referring to. So that's how we got a. So a is 0, we get plus j times delta x, which is 4 over n. So when we go to evaluate this and start figuring it out, simplifying it down nicer, so we're going to go through and kind of algebraically get this as far as we can, then we'll look at what's going on when the limit approaches infinity. This will turn into f of 4 over n times j, because 0 plus 4 over n times j, we could rewrite that as 4 over n times j. We want to evaluate the function at that. The function is just x itself, so what we get is just the stuff in parentheses is what f evaluated that equals. So we just get a 4 over n times j out here. 4 over n is a constant with respect to the sum, so I'm able to push the 4 over n out front. It will multiply with the 4 over n that's already out there, so we'll get a 16 over n squared times the sum of j equals 1 up to n of j itself. So at this point, this is one of our power sums. So if we kind of look, I'm going to use a different color bracket. The stuff in this bracket here, this is one of our power sums. So we're going to go up, and in class we used this form of it and we had to FOIL it out. So I'm going to go and use this second form of the sum of j equals 1 up to n power sum, n squared over 2 plus n over 2. So we'll come down here and say, all right, everything in that parenthesis, that is a power sum, so I can replace it with n squared over 2 plus n over 2. So I can let my 16 over n squared distribute, and I'm going to do a bunch of that arithmetic in my head. So n squared and n squared will cancel. You'll get 16 over 2, which reduces down to 8. In this one, we get 16 over 2, which reduces to 8. You have a single n up top. You have an n squared down below. So that will be plus an 8 over an n. So the one n here cancels with one of the two down there, but there's still a single one left behind. So currently, this is our right endpoint approximation. We want to let the limit as the number of bars we use go to infinity of this right endpoint approximation, which will be the limit as n goes to infinity of this expression 8 plus 8 over n. And if you remember, since n is in the denominator, as n goes to infinity, this becomes 8 over smaller and smaller fractions, like it's 8,000th, then it's 8 millionth, then it's 8 billionth. So this term here, the 8 over n term, goes to 0, and we get that this whole right endpoint approximation turns out to be 8 as the number of bars you use to approximate it approaches infinity. So that right endpoint approximation converges to the theoretical limit of 8, which we got using geometry up there. So we said, okay, right endpoint approximation checks out. What about the left endpoint approximation? If we simplify it and we take its limit as it goes to infinity, will it also converge to 8? And it should, because we have a theorem up here that we covered a bit. It's been a little, where'd it go? Well, here it is. We have this theorem up here that says that they'll all converge to the same limit as n goes to infinity, so this should be true also. So we'll get our left endpoint approximation equals delta x sum of j equals 0 up to n minus 1 f of a plus j times delta x. A is still 0. Delta x is going to be 4 over n. Delta x is 4 over n. So we get the left endpoint approximation is 4 over n sum of j equals 0 up to n minus 1 f of 0 plus j times 4 over n, which we can rewrite as 4 over n. Sum of j equals 0 up to n minus 1 f of 4 over n times j. Again, the function is just x itself, so we get 4 over n series of j equals 0 up to n minus 1. And then instead of evaluating, to evaluate the function, since f of x is x, this will just be 4 over n times j. 4 over n is a constant with respect to j because it doesn't depend on j, so we're able to push it out with the other 4 over n that's there. We get n squared over 16 equals j equals 0 up to n minus 1 times j. So I'd like to use a power sum here, but the problem is this sum here starts at j equals 0, and I need it to start at j equals 1. So what I need to do is I need to write out what the j equals 0 term is by itself. So I'm going to replace j, well, if j is 0, then you replace j with 0, and then we can add to it the rest of the sum, j equals 1 up to n minus 1 of j. So I just wrote the j equals 0 case as an addition by itself, and then I add the rest of the summation over here. This is a power sum, so we're going to be able to replace in this power sum, the stuff in parentheses here is the power sum. So I'm going to be able to replace that all with the power sum equation with n replaced with n minus 1. So if I go up here, I can say n minus 1 is going to replace those n values there. And so what we'll get when we do that, we get 16 over n squared times n minus 1 squared over 2 plus n minus 1 over 2. I need to FOIL this out, and I need to break this up, and I'm going to do some algebraic stuff here to kind of simplify this down. So when I FOIL that top term out, I get n squared minus 2n minus 1, all that over 2. And then I get plus n minus 1 over 2. So I'm going to combine like terms after I break these up. So I'll get n squared over 2 minus 2n over 2. That'd just be minus, you know what, we'll leave it that way. 2n over 2 minus 1/2 plus n over 2 minus 1/2. So as we total this up, we get 16 over n squared. We have n squared over 2. I have minus 2n's over 2 plus 1n over 2. That gives me minus just an n over 2. And minus 1/2 minus another half gives me minus 1. So I get my expression looking like that. I'm going to let my 16 n squared distribute to all three of those terms. The n squareds cancel. 16 over 2 is an 8. When 16n squared hits the middle term, 16 over 2 is 8. 1n up top, 2n's down below, so we get 8 over n, and it's negative. And then 16 over n squared hits the negative 1, so you get negative 16 over n squared. This is our left endpoint approximation. So now we're going to take the limit as the number of bars we use approach infinity of our left endpoint approximation. And what happens is those terms that have n or n squared down in the bottom of them, those fractions will head off to 0 as n grows and becomes infinitely large. So these two go to 0, and we get that the left endpoint approximation also will converge down to 8. So we'll pause on this, and we'll do the last examples in one last one of these. But we get the result we wanted. We showed geometrically the area under the curve is 8. We showed with the right endpoint approximation, as I let the limit as n go to infinity, it converges to 8. And the left endpoint approximation, as I let the limit go to infinity, the left endpoint approximation also converges to 8. So the actual area is what these right and endpoint approximations, they converge to the actual area as the number of bars you use approach infinity.